talking about wavelength modulated sensors lately, and we looked at the example of fiber Bragg gratings, how fiber Bragg gratings can be formed and how can they be used for sensing applications. And we just briefly said that when you want to use this fiber Bragg grating as a sensor, you come in with light at a particular over a broad range of wavelengths. You can interrogate the grating over a broad range of wavelengths, and the grating will reflect around a particular Bragg wavelength, which is given by this expression. And then we said if there is any perturbation that this Bragg grating is exposed to, then there will be a corresponding change in the Bragg wavelength, and that change is what we are trying to pick up to understand the magnitude of the perturbation. Okay, so we will go into this a little more detail in today's lecture. So we will let's look at how we accomplish the sensing using fiber Bragg gratings, and then we will look at a case study. Let's go ahead and design a bridge monitoring system using fiber Bragg gratings. That's what we're going to do in today's session. Okay, so let's start with looking at fiber Bragg grating a little more closely. Let's say this is the core of the optical fiber, where you have refractive index modulation happening at a period of capital lambda, right? And this is happening in the core of an optical fiber, which is of course surrounded by a cladding region. And what we said was we can interrogate this with broadband radiation, and then when you integrate with broadband radiation, what you get as the reflected spectrum is typically something like this. As a function of wavelength, let's say we have a single peak spectrum, so you have something like this, looking at the power as a function of wavelength, and this is happening at lambda b. Now whenever we apply a certain perturbation, of course we also said lambda b is given by 2 times n effective capital lambda. Okay. Now whenever we apply an external perturbation to this grating, so the perturbation may be as strain or temperature, where strain is basically defined as delta L over L, the incremental change in the length of the grating over the length of the grating itself. So this is what we consider as the length of the grating itself, and let's say this is the length over which the fiber is attached to a structure. Now the structure is expanding, then delta L will be a positive number, and if the structure is getting compressed, so delta L will correspond to a negative number, and correspondingly there will be a negative strain perturbation. Okay, and of course we know that you can apply temperature, and that can also cause a change in the Bragg wavelength. But whichever way you look at it, let's say we have this grating shift to a new wavelength from this point, right? So let's say that wavelength shift, we can call it as capital lambda. So now the question is, how can we quantify capital lambda, right? So what is how do you quantify capital lambda, and more importantly, we want to call that capital lambda b because we are talking about change in the Bragg wavelength, right? From from this wavelength to this wavelength. Okay. So, now now let us go ahead and try to see how to quantify that change in the Bragg wavelength. To do that, basically you can take this expression and then you can differentiate. So, you can say delta lambda b would consist of some change in lambda b with respect to the rate of change of lambda b with respect to strain for an applied change in strain, and then similarly you could also have a rate of change in the Bragg wavelength per unit change in temperature, and that of course would have to be multiplied by the change in temperature itself. And that is actually one of the key things that we need to understand, that the Bragg wavelength is sensitive to both strain and temperature changes. So, that is like we talked about earlier, that is one of the primary challenges when we talk about doing sensing using fiber Bragg gratings. It's not easy to discriminate between changes in strain and temperature. But anyway, if we go ahead and try to expand this, lambda b is given by this. So, we understand that any change in strain can of course change the period, because physically you have say stretching the fiber, there is a physical change in the capital lambda, but there is also a change in the effective refractive index, and that is through an effect called strain optic effect. Okay. And similarly, when we talk about the change in lambda b with respect to temperature, you have one change which is change in capital lambda, the period, which will correspond to what is called the thermal expansion coefficient. That is more commonly known. But what's not as commonly known is the fact that the refractive index also changes, and that is called the thermo-optic effect. Okay. So, if we write this in terms of changes in refractive index and changes in period, we can just say you have one component which is 2 times n effective d capital lambda over d epsilon, right, plus you have 2 times capital lambda dn over d epsilon, right, the change in refractive index with respect to strain, and this is what we call as the strain optic coefficient. So, the whole thing multiplied by delta epsilon now, and then of course, the other part where you can say it is 2 times n effective, you have the thermal expansion coefficient, which results in a change in the period with respect to change in temperature, plus you have 2 times capital lambda dn over dt, which is the thermo-optic coefficient, and the whole thing is multiplied by delta t. Okay. Now, of course, you can take out a common factor from all of this. Let us say you take out 2 times n effective times capital lambda, which of course corresponds to the Bragg wavelength itself. Then you can just say this is this first term will be 1 over capital lambda d capital lambda or d epsilon plus 1 over n effective dn over d epsilon multiplied by delta epsilon, plus similarly you have 1 over capital lambda d capital lambda over dt plus 1 over n effective dn over dt, whole thing multiplied by delta t, and this appears as a common term. So you have taken this term, which is which we know corresponds to lambda b. So delta lambda b is a fractional change around lambda b because of all these factors. So I can write all these factors. This is actually what is called the linear expansion due to strain, and this is actually the strain optic coefficient, right? And similarly, this is your thermal expansion coefficient, and this is your thermo-optic effect, right? So you have all these contributing to a possible change in the Bragg wavelength, and of course you can quantify this for the case of silica, and what you find is for the sake of for silica, this works out to be approximately 1.1 picometer per microstrain, right? So that's the value, that's the coefficient if you plug in the coefficient for the linear expansion as well as the strain optic coefficient. And similarly, if you calculate this factor within the parenthesis, that actually works out to be roughly about 13 picometer per degree centigrade. Okay, so those are fairly small numbers. We're talking about picometer changes in the Bragg wavelength. So that is one of the challenges as far as picking up this perturbations using this fiber Bragg ratings. How we can pick up even small changes like 1 picometer, and mind you, the wavelength that we are using let's say is 1550 nanometers. So you're talking about changes in the wavelength around 1550 nanometer to the level of 1 picometer per microstrain. Okay, but of course, if you are able to pick that up, you can say that it is due to perturbation at the grating location, and that's because of the fact that the this wavelength information is not corrupted by all these traditional noise sources. Okay, so that's the advantage we have, but nevertheless it is a challenge to pick up such small changes in the wavelength itself. Okay, so let us now go ahead and try to design a system. Okay, so let's say we are going to go ahead and try to design what is called a bridge monitoring system. So it is a fact, it's an interesting fact that India has tens and thousands of bridges that are built around the country, and more than half of them are fairly old bridges. Several of them actually built during the British era, right? So these are bridges that have been standing there for more than 100 years in some of these cases, right? So it is really a very important requirement that we need to monitor the strength of those bridges. We need to monitor them for if there are any cracks that are developing in these bridges, and if there are cracks developing the bridges, then you actually do some reinforcement so that it doesn't propagate, and we can prolong the life of the bridge as we go on. So that's to do that, you need to actually have a sensor which can monitor the health of the bridge across the entire span of the bridge. So and one possible solution that a lot of people are considering is use of fiber Bragg ratings for these applications. So this is the requirement. So let us design a condition monitoring system for a bridge. Let's say it's spanning let's say 100 meters, okay, and let's say you are asked to provide real-time data on the strain that it undergoes, right, on strain at any location along the bridge with a spatial resolution of let us say 2 meters. Every 2 meters you need to make a measurement of the load that you have in this on this bridge, and you need to do that in a real time manner, right. So real time, let's say we have to provide the data points, the load data on the bridge every second, once every second. Okay, so that's the kind of requirement you have, and we need to assume a certain load, or we need to classify that there is some the work that needs to be done on the bridge. So we need to define a threshold level in terms of the load at any particular point on the bridge. So let us assume a maximum loading of plus or minus 1000 microstrain. So if it goes beyond 1000 microstrain, then you are supposed to raise an alarm, but up to that point you are supposed to just give a value at each point along this bridge. Okay, and of course when you're trying to measure strain, you're also having to contend with changes in temperature. So we can assume that assume a max loading of 1000 microstrain plus or minus, and temperature variation of 15 degrees centigrade over a period of 24 hours. Okay, so that is the let us say that is the requirement. So you need to monitor over 100 meters with 2 meter resolution. So how many gratings do you need? So how many measurement points do you need? You need 50 measurement points, right, across the bridge, and let's say they're all uniformly located, and you need to expect that the strain variation could be up to 1000 plus or minus 1000 microstrain, and we need to also contend with temperature change of 15 degrees centigrade. So let's go ahead and try to visualize this problem. Of course, you find that when you visualize this problem, you are able to provide a solution. You can have an intuition as to how the design should work out. Okay, so let's go ahead and try to do that. Let me just go to a fresh page and do that. Okay, so we are talking about having a long length of fiber. So this is spanning 100 meters, right? So we know that in fiber Bragg grating based sensing system, you can concatenate gratings. You can concatenate gratings with different periods, so that you can actually use one broadband source and integrate the entire length of fiber, which consists of gratings at different wavelengths. Okay, so and where should all these gratings be? Well, basically they need to be 2 meters apart and so on, right? And so we need to have 50 of these gratings. So this one should be, let's say, lambda 1, lambda 2, lambda 3, lambda 4 and all that, right? And lambda 49, lambda 50. So one possible solution is that you have 50 different gratings that are reflecting, that are with different periods, and so hence they are reflecting at different wavelengths. Then you can possibly integrate them with one broadband source. Okay, and what we are talking about here is the physical location of these gratings. Let's say these are attached to the structure, right, attached to the bridge at these locations, and these physical locations are separated by 2 meters. Okay, the center to center spacing, it's 2 meters, and like we looked at previously, each of these gratings, as we considered in one of these examples over here, each of these gratings is typically like in the order of millimeters. So you can paste that, and then at that particular location you can actually figure out what is the strain that's developing. Okay, so in terms of the spectrum, how does that look? If we look at the spectrum along this entire length, so if you look at this, if you integrate the grating without any perturbation, what we are going to see is you will have one grating at let's say lambda 1, it's centered around lambda 1, and another grating centered at lambda 2, then another grating centered at lambda 3, lambda 4 and so on, and something corresponding to lambda 49 and something corresponding to lambda 50. Right, so you will have a lot of these grating peaks. So if you send in broadband light and you look at the reflected spectrum, you will see all these peaks. Okay, and then the question is, what should be the spacing between the peaks, right? So that's something that we need to decide. And how do we decide that? Well, we need to consider the fact that each of these gratings can be undergoing a perturbation of 1000 microstrain. So, it could be negative strain or positive strain. So, but it could be 1000 microstrain. So, what does 1000 microstrain correspond to? We know that these gratings have a typical strain coefficient of 1.1 picometer per degree centigrade. So, you have 1.1 picometer per degree centigrade multiplied by 1000 sorry, it is not degree centigrade. In this case, we are talking about microstrain with respect to strain. So, 1.1 picometer per microstrain and that is over 1000 microstrain. So, that corresponds to on one side, just this side itself, it corresponds to 1.1 nanometer, right. So, this is 1.1 nanometer, this is 1.1 nanometer on the other side as well, right. So, the spacing between the two Bragg gratings has to be now 2.2 nanometer at least. I mean, larger the better, because that way you will make sure that the peak that you see corresponding to strain at one point is not overlapping with the peak corresponding strain at another point. Okay. So, you want to be at least so let us say greater than equal to 2.2 nanometer spacing that you are going to have to do. And of course, you are doing this over 50 gratings. So, the entire spectral width from here to there, so that will correspond to 110 nanometers, right. So, you need to be able to integrate over 110 nanometers. Okay. So, that is nice, but what is the kind of let us go ahead and try to see what is the kind of signals that we expect at any of these grating points. So, let us say at location 1, which corresponds to Bragg wavelength of lambda 1. So, how does this the change in Bragg wavelength look in terms of with respect to time? So, on this axis, let us say we are looking at time in let us say days. So, talking about starting from 0 here, 1 here, 2, 3, 4 and so on, right. So, what do we expect in terms of this axis? It's in lambda, right. So, you are measuring, so let us say you have some way of measuring lambda, right. So, of course, if you look at lambda 1 at location 1, it is going to be let us say at minimum temperature, at ambient temperature or minimum ambient temperature at any particular day, it is actually at lambda 1. But of course, we know that it is going to change over this 24-hour cycle, right. So, and the rate at which it changes 13 picometer per degree centigrade, and we know that the temperature change can fluctuate over 15 degrees. Let us say this is the lambda 1 that you measure in the early morning hours. During the course of the day, the temperature is going to increase, and correspondingly you will have a change in the Bragg wavelength. Okay. So, and let us say we look at this on a daily basis, section by section, 24-hour sections. Okay, so it's going to now increase during the day, right, go to a particular point, and then of course decrease as the sun sets and you go towards the night. And then of course the next day similarly you will going to have an increase and then a decrease, an increase, a decrease, and so on. So this is what we expect, and it goes up. So what wavelength does it go up to? So this, let's say this is the maximum temperature it reaches on any particular day. So this wavelength is going to be lambda 1 plus some delta lambda, and that delta lambda you can actually figure out. We are expecting 15 degree change in temperature multiplied by the rate at which the Bragg wavelength changes with respect to temperature. Let's say it's 13 picometer per degree centigrade. Mind you, that is actually a rough number. In reality, it depends on the constituents of the fiber, or what the actual fiber is made of, and then what are the type of doping that you have incorporated to increase the photosensitivity of the fiber. So all those things actually come into the picture. But nevertheless, if you assume it's 13 picometer per degree centigrade, then that works out to be roughly about 0.2 nanometer, right. So you have a 0.2 nanometer shift in Bragg wavelength because of this. Now of course due to strain you do expect a lot of changes that are happening, and to put that in perspective, we are expecting up to 1000 millistrain sort of changes over the period of the day. And of course what is important is that this temperature change does not affect the measurement at some other wavelength. So in this case we are considering lambda 2. Where is lambda 2 with respect to lambda 1? That is going to be lambda 2 is given by lambda 1 plus what we decided here was it has to be 2.2 nanometers. So if lambda is in nanometers, so that's actually 2.2 nanometers away. Okay, so the temperature change by itself is not actually causing a huge problem, but nevertheless it can cause a problem at this other wavelength, because now this 0.2 nanometers is not something that we have accounted for here. So do we have to worry about it? Well, let's actually look at the real time changes in the Bragg wavelength as a function of time. So what we typically have a case where the Bragg wavelength is changing because of loading conditions during the day. Okay, so it will tend to fluctuate around this value depending upon, for example, the traffic that the bridge is seeing. So during the early days the traffic is not as much, but during the middle of the day and during maybe peak hours you see a lot of traffic, and then it comes down during the night, and then it's like this, right. So you might have depending upon the traffic all these changes that we are expecting, right. So you have all these, so these are due to strain at at you know at location 1, at location 1 due to the load experience, right. So that is one thing to note here, and of course we are saying, when does this go beyond say 1000. So we say the threshold level for this perturbation is somewhere in the middle. So this is actually at 1.1 nanometer, lambda 1 plus 1.1 nanometer. That's where the threshold is. So we are trying to see if it actually reaches that threshold during the day, right. That's what we want to find out. And of course, if there is a pattern like this where it goes up and comes back, you're not too worried about it. That you say is the dynamic load on the structure. What you are worried about is if it doesn't, when it comes back, it doesn't come back to the same point, right. If we end up actually after day 1, it ends here, after day 2, let's say it ends here, after day 3 it ends here, and so on. It's actually having some incremental change in the loading on a day-to-day basis. Then you can clearly say that this is actually at location 1 there is a crack that's developing, and it's getting wider and wider by the day, right. So then you will clearly see a signature where it's not coming back to this point, it's actually going up and then coming back here, going up and coming back here, going up and coming back here, and so on, right. So then there is actually some intervention that's required. You need to go back and do some reinforcement work. Okay, but this is the interesting part. The question is, should we account for this 0.2 nanometer change in temperature? And it turns out you don't have to, because this is at lambda 1, but let's say what's happening at lambda 2, if you look at it, lambda 2 would also have a similar sort of fluctuation. It's going up and then it's coming down as over that day, and then it's going up and then coming down as the day progresses towards the night, and similarly and so on, right. So you will have these traffic, and towards the night it comes down. So it's going to be like this. But the key point is, whatever temperature that change that lambda 1 is experiencing, the grating with the center wavelength at lambda 1 is experiencing, that almost the same temperature profile the grating at lambda 2 is also experiencing. So in this sort of a scenario, if you understand that there is no differential in the temperature across a bridge, there may be some momentary changes in temperature, but over a period of 24 hours there is hardly any change in temperature. So then in that sort of a scenario, you don't necessarily need to compensate for this 0.2 nanometers. But if you have an industrial process where the temperature that you see at lambda 1 can be very different from the temperature that you can see at lambda 2, and so on, in those sort of cases you want to actually make sure that you can account for that, and correspondingly design your next lambda to be at slightly longer wavelength. The spacing between the different Bragg ratings in terms of the spectrum is actually more accounting for that change in temperature as well. Okay, so this is the kind of measurement design challenges that you will be posed with, and then of course by looking at it systematically, by looking at the bigger picture, understanding the requirement first in terms of placement of the gratings, that is very important, and then you go into what should be the for a given requirement, what should be the spacing in terms of the spectrum between the different gratings, and then you go on to actually do some simulations as to what sort of load profiles that you expect, and then make sure that there is very little source of uncertainty in terms of measuring these loads, and that's basically what constitutes the design of the system. Now, of course, so far we have assumed that we have something. So this is actually you are sending in some light, and you are interrogating the backscattered light, or the light that's scattered from this Bragg gratings. So this we have assumed it's a broadband source, but then how do you actually pick up the spectrum of all these gratings, right? So you need a wavelength demodulation. So far we have assumed that the wavelength demodulation is available to us, but what we want to understand is what are the common ways of actually doing the wavelength demodulation. How do you do this entire interrogation of these Bragg grating sensors? Okay, and that is what we will look at in the next lecture.